All right, good morning, everyone, and welcome back to Lecture 2 of Constructive Mathematics. I'm still Patrick Farrell, that hasn't changed. So last time, on Tuesday, we started this course with some sort of philosophical remarks about how the conception of what does it mean to solve a mathematical problem has changed over the years, in particular with Abel's theorem that there is no closed form formula for the solutions of a quintic polynomial. And so in continuing in that vein, I thought I would read out something to you. So a previous colleague of mine here in the department, his name was Nick Diophantine. He was the professor of numerical analysis. Now he's gone to Harvard as of last year. He wrote a book of philosophical musings and observations, and this is one of them that resonated with me, and I'd like to read it out to you. What does it mean to solve a problem? At ANU is the Australian National University in Canberra. Recently, I had lunch with some mathematicians. One of them, Terence Tao, who's one of the most famous mathematicians alive, pointed out how profoundly our views have changed with the years. Traditionally, he said, to solve a mathematical problem meant to prove existence of a solution. Modern developments, however, have transformed our thinking, and it is now recognized that an equally valid idea may be that to solve a problem is to elucidate general geometric and topological features of solutions of problems of that class. And Nick goes on to write, there was no mention of a third idea. One might say that to solve a problem means to actually calculate the answer. I wonder whether this notion will catch on. Now, I might have phrased it a little bit differently. I might have said that to be able to solve a problem means that you're able to solve any instance. You don't need to have solved all potential quadratic equations to know that the quadratic formula solves for the roots of quadratic polynomials. But nevertheless, I think there's a lot of merit in that point of view. Now, of course, there's also great wisdom in the point of view expounded by Terence Tao. But at least for our purposes in this course, for 2 hours per week, for 1/2 of one of 3 of your terms, this is the point of view that we'll take. That to solve a problem means to be able to efficiently calculate the answer. Okay, so let me remind you where we were and what we were doing. So we started off by asking, what kinds of questions do we ask about algorithms? Algorithms being the central stars of our show. And then we thought that we would begin our study of algorithms by meeting lots of different examples. And the first example that we met was Euclid's method for computing the greatest common divisor, or the highest common factor, of 2 numbers. Okay, and here it is stated as an algorithm. And it proceeds by iterated division, or at least as stated here more precisely, by iterated computation of remainders on division. In this algorithm statement, I don't use or need the quotient, so I don't write them down. And it's worth just recalling, why is this an algorithm rather than a formula? Well, the reason is because for any given input, you might have a different number of operations to do. If I give you sufficiently big inputs, you'll have to do sufficiently many operations. Whereas with a formula, the number of operations you have to do is bounded. Here, this involves iteration. You have to keep going until something is satisfied. And that's what makes it an algorithm rather than a formula. Okay, so we met this algorithm, and we proved various things about it. We showed that it terminates. We then showed that what this algorithm returns, its output, is a common divisor, at least, of the 2 inputs. And then we proceeded to prove that its output was the greatest such divisor, the greatest common divisor. And then once we had proved correctness, in this case without any qualms or qualifications or any conditions to meet, this is just unambiguously a good thing, then we discussed its complexity. How many operations does it take? And we met the interesting observation, due to Gabriel Lamé, that the worst case inputs for this algorithm were 2 adjacent entries in the sequence of Fibonacci numbers. Okay? And just to remind us of how this algorithm goes, I thought I would run the algorithm on some instances of entries of the Fibonacci sequence. So 13 and 8, for example, are 2 adjacent entries of the Fibonacci sequence. and you notice something interesting about the remainders, that 13 divided by 8 plus 5, where 5 is the lower entry, the previous entry in the Fibonacci sequence, and then 8 divided by 5, remainder 3, where that's the one down in the Fibonacci sequence, and so on, so that if, for example, we do 21 and 13, so the next two entries in the Fibonacci sequence, the sequence of remainders just returns to us each Fibonacci number in turn, right? And it's because, of course, now that you do the computations, it's fairly easy to see. The reason is that the defining recurrence relation for the Fibonacci equation is that fn plus 2 is equal to fn plus 1 plus fn. And if I put a 1 here, that's the quotient, and that's the remainder. So this is the statement of the division of one Fibonacci number by the previous. And so that's why the Fibonacci numbers are sort of the worst case complexities, and that's how you can get Euclid's method to do as many iterations as you like by going far enough along the Fibonacci sequence. Okay, that's where we were. So today we're going to see what else can we use Euclid's method for beyond just computing greatest common divisors. And it turns out that we can use Euclid's method for solving really important and useful problems. In fact, problems that your computer has probably solved on your behalf many thousands of times. And these will show up as Diophantine equations. Okay, so what is a Diophantine equation? So it's an algebraic equation for which we look for solutions in the integers, okay? So I'm going to write down an equation. I'm not going to look for any old solutions, real numbers or rationals or complex numbers. I only want integer solutions. And these are named after Roman Greek mathematician Diophantus of Alexandria, who was working in Alexandria, the same place where Euclid was, but about 600 years later. Alexandria was a great center of learning for a very, very long time. Okay, and so some Diophantine equations have no solutions, right? So if I give you the problem, find x and y such that 4x plus 6y equals 3, it's fairly easy to see that there can't be any solutions of this problem. And can anyone tell me why? Yes? Exactly. The left side must always be even no matter what choices for x and y that I make. The right-hand side is odd, so there can be no solutions. Some Diophantine equations do have solutions, of course. 48x minus 35y equals 1 has a solution. Here it is. X is minus 8 and y is minus 11. And we'll learn how to compute such solutions today. And of course, Diophantine equations don't have to be linear, right? So probably the most famous Diophantine equation is the equation arising in Fermat's last theorem that x to the n plus y to the n equals z to the n. I'm not just looking for any old numbers x, y, and z. We're looking for integers. Okay, and in fact, Fermat's last theorem has a very nice connection to Diophantus. So Diophantus's work was accumulated in this great book, his magnum opus called Arithmetica, which mostly survived in libraries and monasteries in the Byzantine Empire. And in 1637, Pierre de Fermat, he was reading his copy of Arithmetica, and he wrote the famous text in the margin. I'm sure you've seen it before. It is impossible for any number which is a power greater than the second to be written as the sum of two like powers. In other words, Fermat's last theorem. I have a truly marvelous demonstration of this proposition, which this margin is too narrow to contain. So the book in which he wrote this was Diophantus's Arithmetica, and he was thinking about Diophantine equations because he was reading Diophantus's work. And of course, this has a strong connection to us because this lecture is coming to you live in the Andrew Wiles building, who proved Fermat's last theorem. Okay, so let's be more precise about what it is that we're looking for. We're interested today in linear Diophantine equations. So it's a linear equation in two variables. So given a, b, and c, I want to find x and y such that ax plus by equals c. Okay, and of particular interest are when the a and b are coprime, when their greatest common divisor is 1, and when 1 is on the right-hand side. And why is that? Well, in particular, if we can solve ax plus by equals 1, so we can find x and y so that this holds, then we've also solved the problem, find x in the integers such that ax is congruent to 1 modulo b. Okay, so this means that x is the inverse of a modulo b. So this is the task of finding modular multiplicative inverses. And why is this useful or important? Well, in particular, this is very commonly used in cryptography. So for example, this is a crucial step in RSA key generation, sort of the first practical public-private asymmetric cryptography scheme. Okay, so you've chosen your public key, which are two numbers, n and e, where n is the product of two very large primes. And then you want to compute the private key, the thing that you will use to decrypt the messages that you receive. And in order to compute the private key, exactly the task at hand is to compute the modular multiplicative inverse of e modulo a function of n, the Carmichael-Totient function, where the thing is that lambda of n is very easy to compute if you know the prime factorization of n, and it's extremely difficult otherwise. Okay, and so when you're making your key pair, you first generate the public key, then you compute the associated private key exactly by solving the problem that we will solve today. Okay, so let's first look at an existence result for such equations. Okay, and so this lemma is known as Bézout's lemma. If the greatest common divisor of a and b is d, then the linear Diophantine equation ax plus by equals d always has solutions. Okay, so this is an existence statement, and we will prove it with an algorithm. Okay, so this statement for integers was already well known before Bézout. It appears, for example, in the work of a guy with a wonderful mustache, Claude Gaspard Bachet de Méziriac, in 1624. And Bézout's contribution was really to extend it to polynomials, and thereby to kind of more general algebraic structures, something we'll touch on at the end of this lecture. But nevertheless, his name has stuck to the general principle, right? Normally in maths, when something is named after someone, they didn't do it first, right? So Euclid's algorithm, Euclid was the guy who wrote it down, but almost certainly the algorithm existed before. Bézout's lemma, Bézout was not the first one to write it down, but nevertheless, that's what we call it. And what's interesting, if you're interested in studying algebra further, is that many, many other results in number theory follow from Bézout's lemma, such as Euclid's lemma that if a prime number divides a product AB, that it must divide at least one of A and B. That's Euclid's lemma. And the Chinese remainder theorem, or Sunzi's remainder theorem, it always kind of struck me as odd that we say Euclid's name for Euclid's lemma, but we don't say Sunzi's name for the Chinese remainder theorem. We don't say the Greek lemma about reconstructing numbers if you know the remainders on division. Okay? And so if you have an algebraic structure where Bézout's lemma holds, then immediately you get all kinds of interesting other results in other structures for free. Okay, let's go ahead and get the idea of Bézout's lemma. Why will this hold? Right? And then sort of the proof that I'll give is just kind of the formalization or the statement in abstract variables rather than concrete ones. Okay, so let's do an example. So let's take 48x minus 35y equals 1 that we saw earlier. So I already told you that the solution was minus 8 minus 11. So what are we going to do? We're going to apply Euclid's algorithm to the two natural numbers in this problem, so 48 and 35. And we already know, or maybe we don't, that these are coprime. So their greatest common divisor will be 1. So this sequence of divisions that we're going to write here on the left will eventually terminate with the 1 in the bottom right. Okay. But let's go through the steps of Euclid's method regardless. So we say that 48 is 1 times 35 plus 13. And then here on the right, I'm going to record the remainders arising in this equation. Okay, so I'm just going to rewrite this equation as 13 equals 48 minus 1 times 35. Okay, and then we proceed to divide 35 by 13. 35 is 2 times 13 plus 9. So that means that 9 equals 35 minus 2 times 13. We go again. 13 equals 1 times 9 plus 4, which means that 4 is equal to 13 minus 1 times 9. And then for our final division, we have 9 equals 2 times 4 plus 1, which means that now we have an expression for 1 in terms of 9 and 4. All right, and so in order to compute a solution of this equation, what we want to do is we want to express 1 in terms of 48 and 35. And 48 and 35 were the two top entries in our sequence of remainders constructed by Euclid's method. Here, at the last step, I have 1 expressed as a linear combination, an integer combination of 2 remainders in the sequence, but the bottom 2. And so now I need to work my way back up the equations, substituting each of these in turn. Okay, so I take this equation, 1 equals 9 minus 2 times 4. And then from this here, I have an expression for 4. So I can substitute that in and simplify. So now I have 1 written in terms of 13 and 9. So I've moved my window of that I'm taking of the remainders 1 step up. And then I do it again, so I have an expression for 9. I substitute it in here. After I simplify, I have 1 expressed as a combination of 35 and 13. And then I have an expression for 13 in terms of 48 and 35. So I substitute that in and simplify. And then I get minus 8 times 48 plus 11 times 35. And then I notice that, hang on, the task I had was minus 35, so I need to negate this 11. Okay, so that's how you do it. You climb up the tower of equations on the right-hand side, substituting in expressions for the remainders. Okay, so let's make that slightly more formal, not too much more formal. How do we prove Bézer's lemma? We run Euclid's method. So since we know already the greatest common divisor of our two numbers, we know that if we keep dividing, eventually, so we write A is a quotient times B plus a first remainder, B equals Q1 R0 plus R1, and so on, and we keep dividing, we will eventually reach an equation of this form that Ri minus 3 is equal to Qi minus 1 Ri minus 2 plus D, where D is the greatest common divisor. Okay, and so then we can just rewrite that equation as D equals some integer combination of the previous two remainders. And then we use the next equation up to write D as an integer combination of the next two remainders in the sequence, going back up, and now in terms of Ri minus 4 and Ri minus 3. So this is 4 off the bottom and 3 off the bottom. And then if you proceed by induction, which of course you can make formal, you can write D as an integer combination of Ri minus 5 and Ri minus 4, Ri minus 6 and Ri minus 5, and so on until you get to the top two remainders in your sequence, which were the numbers that you wanted in the first place. Okay? And so this uses an algorithm to prove an existence result, right? And so this is very, very common. Even if you never intended to ever actually solve a linear Diophantine equation, if you were just, for example, interested in the existence of modular multiplicative inverses, you would use this algorithm to prove solutions to the linear Diophantine equation, and then you would have the existence result that you desired. Okay, and so we saw already that this LDE has one solution, but of course there are other solutions. And normally as a mathematician, you're not happy until you have got every possible solution that you could have. Okay, and so you can play around with your calculator or with your computer and find other solutions. For example, like x is minus 43 and y is minus 59. How do we find them all? Well, as usual, knowing a particular solution for a linear problem usually means that you can crack it open and find all solutions. So, okay, so suppose we have a particular solution, xp, yp, satisfying axp plus byp equals 1. All right? And then if we could find solutions to the associated homogeneous equation, this is just, for example, like how you think about general solutions to differential equations, to linear differential equations. You consider the problem with 0 on the right-hand side. If we had such an expression, then I could add this equation, and you would get a into xp plus x tilde, b into yp plus y tilde. Well, when you expand out the brackets, that ax tilde, by tilde cancel. They're just 0. And so you're left back with 1. And vice versa. If you do have another solution to the LDE, then you can conclude that ax tilde plus by tilde equals 0. Okay, so all the solutions are a particular solution, and then the solutions to the associated homogeneous problem. And what are the solutions to this homogeneous equation, ax tilde plus by tilde equals 0? Well, I could just choose x tilde to be b, and choose y tilde to be minus a, or the other way around, minus b and a, and then that would always give me 0. Or I could take integer multiples of those. And so the solutions of the associated homogeneous equation are exactly integer multiples of minus b a. Okay, and so that means that the general solution to ax plus by equals c is thus c into the particular solution, because this was a solution, the particular solution satisfied 1 on the right-hand side. But now if I have c on the right-hand side, I should multiply the particular solution by c, plus some integer multiple of minus ba. Okay, so before I lectured constructive maths, I tutored it at Oriel. And my experience was that about half of my tutees, of course on the problem sheets you have a lot of LDEs to solve in order to get the gist of it. And my experience was that about half of people weren't doing it right. And the reason was because the lecturers didn't actually state sort of the whole procedure for solving the LDE. So here I thought, now that I get the chance to lecture it, I would tell you the whole procedure for solving the LDE. Okay, so we're given an LDE ax plus by equals c, and we're not making any assumptions about it. Okay, so the first thing that you have to do is to run Euclid's method to calculate the greatest common divisor of a and b. Okay, and we'll call that d. If d doesn't divide c, then you stop. There are no solutions, because the left-hand side must be divisible by d, but the right-hand side is not divisible by d, so there are no solutions. If c is divisible by d, then you divide both sides of the equation to get a hat x plus b hat y equals c hat. So this is where we factored out the greatest common divisor from all the terms. That's the hats. All right, so then I'm going to compute a particular solution of a hat x plus b hat y equals 1. So you forget c hat for a moment, solve the problem with 1 on the right-hand side. And how do we do that? We run Euclid's method again. So this involves running Euclid's method twice. Okay, and then you set the general solution to be c hat into the particular solution you calculated here, plus n into minus b hat a hat. Okay, and that's the general solution to this problem. Okay, so let's just consider an example and go through those steps. So let's consider solving 192x minus 140y equals 12. Okay, so step 1 is to calculate the greatest common divisor of 192 and 140. And when you run Euclid's method, it turns out to be 4. Okay, and then we check, is 12 divisible by 4? Yes, it is. So there are solutions, so we can proceed. Okay, and so then we divide both sides by this number, by this greatest common divisor. We get the reduced problem where now these two are coprime. 48x minus 35y equals 3, which conveniently we've already seen. Okay, and so then we solve the problem with 1 on the right-hand side to get our particular solution. So, and we've already seen how to do that. So we get xp, yp is minus 8 minus 11. And then we write down the general solution. So the general solution is 3 times this particular solution, because I've got 3 on the right-hand side here, plus n into minus ba, or the other way around. It doesn't matter. Okay, and so those are the general solutions to this linear Diophantine equation. Okay, so now let me just go back to Euclid's method for a moment. And what we're going to do is we're going to tweak it a little to make the calculation of solutions to this linear Diophantine equation much more convenient. And that variant is called the extended Euclidean algorithm. Okay, so we've already seen that the quotients computed during the run of Euclid's method tell us how to solve the linear Diophantine equation ax plus by equals the greatest common divisor of a and b. And this is, by the way, like, something really interesting philosophically. That Euclid's method on its own didn't require the quotients, but the quotients turn out to be really useful for solving related problems. And so one thing when you're studying algorithms or when you're devising an algorithm, one thing that you should think about is take a look at everything that you're computing and ask, is it useful for something? Am I computing some byproduct that could be useful for something else? Okay, but the way that I phrased it, of sort of climbing up the tower of equations backwards, it's intuitively useful, and that's the way I would do it if I was doing it on paper. But it's not so amenable to computer implementation, right? And why is it? Well, for a start, it requires storing all of the quotients and all of the remainders that we went through in all of the steps, right? So rather than having constant amount of storage required to execute the algorithm, I have storage proportional to the number of divisions that I have to do, and I don't like that. The complexity is worse. And there's a very clever modification of Euclid's algorithm that computes the particular solution to this LDE, the special LDE with the greatest common divisor on the right-hand side, and it computes it in one pass with optimal storage, with constant amount of storage, and that's called the extended Euclidean algorithm. And that's what we'll meet now. Okay, and this appears to have first been explained by an Indian mathematician working in Bihar, Aryabhata, in the late 400s or early 500s. He didn't exactly phrase it as working on linear Diophantine equations, but rather working on problems that were equivalent. And the name that he gave the algorithm I thought was really charming. He called it the Sanskrit word for pulverizer. I thought that was a very good exercise in branding. Okay, so here's the idea of the extended Euclidean algorithm. Okay, so Euclid's algorithm constructs a sequence of remainders, r minus 2, r minus 1, r naught, r1, dot, 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 up to r minus 1, where this is the final guy. This is the greatest common divisor of a and b. And again, we'll denote r minus 2 is a and r minus 1 is b, just to emphasize that a and b are the top two entries in this sequence of remainders. So the key idea of the extended Euclidean algorithm is to introduce two new sequences called x and y. And these are going to have a very nice property. And what is that property? These will store the coefficients of the expansion of a given remainder in terms of the original entries a and b, in terms of the inputs to our algorithm. Okay, so at every step of the algorithm, I'm going to compute the coefficients that express any given entry of this sequence of remainders as the integer combination of a and b, and then in particular the final entries of the sequence x and y will be the coefficients that tell us how to expand ri minus 1 in terms of a and b, and remember that ri minus 1 is the greatest common divisor. So these will form the solution of the linear Diophantine equation that we're trying to solve. So we're just going to expand every remainder in terms of, think of it as a basis, as a combination of a and b. Okay, so how do we enforce this invariant, this property that holds throughout all of the iterations, that a times xj plus b times yj equals rj? Okay, well, let's think about how we enforce it at the start. At the start, I should initialize my sequence with x minus 2 and y minus 2 should just be 1 and 0, because this says that ri minus 2 is 1 times a plus 0 times b, right? And ri minus 2 is just a, so that's just recording that fact. And similarly, x minus 1 and y minus 1 should be 0 and 1, because this is saying that ri minus 1, the associated remainder, is 0 times a plus 1 times b. Okay, so that's just, again, expressing the expansion of ri minus 1 in terms of b. Okay, and so we know how to start our sequence of x and y's. And then if we consider some step of Euclid's method, so here's sort of the general form for one of these divisions that we write rj is q, j plus 2, rj plus 1. So we've divided rj by the next remainder, and we've got this quotient here and this remainder here. So if we know the expansions of rj and rj plus 1 in terms of our basis, in terms of a and b, then we can work out the expansion for rj plus 2 also. So you can think of this as sort of, I'm expressing every entry in the sequence of remainders as a linear combination of my two basis vectors a and b, and so you can think of this as just an equation for the coefficients of rj plus 2. And so in particular, the x coefficient of this guy is just the x coefficient of that guy minus the x coefficient of this, multiplied, of course, by the quotient, and the same for the y's. Okay, so that's very, very nice. Okay, so let's take a look at how this looks in the code. So here is the extended Euclidean algorithm. So what does it look like? Well, I just do some checking at the start to make sure that my assumptions are satisfied. I initialize my sequence of remainders with a and b. I initialize my sequence of x and y's with 1, 0, and 0, 1, just expressing those remainders in terms of my original inputs, a and b. And then now I loop until I'm done. So here I only ever need to store 2 entries of each sequence, right? I don't need to store the whole of the r's, the whole of the x's, and the whole of the y's. I'm just going to store 2 of them at a time, so sort of a shifting window in this sequence. So until I'm finished, while this remainder is greater than 0, I compute the quotient by dividing the previous remainder by the next remainder in the sequence. And then I compute the next remainder in the sequence is the previous remainder minus the quotient times r next. So that's computing the remainder on division of r prev and r next. And then I just do the exact same to the x's with the same quotient that I've computed here, the exact same to the y's with the same quotient that I've computed here. And then I'll add this assertion so that the Python interpreter will check for me that my loop invariant is indeed satisfied at every loop, at every iteration. And then once I'm done, I return the greatest common divisor, which is the last remainder before it hits 0, and then the associated combinations of coefficients. Okay, and so for example, if I run this on, I don't know, 48 and 35, then we get exactly the coefficients that we had before, minus 8 and 11. So if I was thinking about minus 35, I would have minus 11. Or you can pick some other example of 7 and 3, that 7 times 1 plus 3 times minus 2 equals 1. So this is a very, very nice way of computing the solutions to the particular linear Diophantine equation that you have to solve just in one pass with an optimal amount of storage. You treble the amount of numbers you have to store in running Euclid's method. Okay, so now that we've seen one extension of Euclid's method to solving linear Diophantine equations, let's now extend it in a different direction and take a look at what it looks like for other kinds of algebraic objects. And in particular, we'll need it for computing greatest common divisors of polynomials. Okay, and so as we've said, we've applied so far Euclid's method to integers, but it applies to other kinds of algebraic objects too. So let's meet such an example. A polynomial p of degree d, so I'll denote the set of polynomials with real coefficients in sort of the dummy variable x with this notation here. It's an expression of the form a0 times x to the 0 plus a1 times x plus a2 times x squared up to ad times x to the d, where all the ai are drawn from the underlying field, where they're all drawn from this set of real numbers. Now, of course, that's a perfectly fine definition. It's all the functions of that form. As I mentioned on Tuesday, you would never want to store any given polynomial with this representation because it's wildly unstable, but for theoretical purposes, it's perfectly fine. Okay, and so recall that a root p, a root of p is a number x satisfying p of x equals 0. And just like with integers or natural numbers, we can divide one polynomial by another. So now I'll call the polynomial I'm dividing by q. I hope that's not too confusing. Q used to be the quotient. Now it's the other polynomial. It seems natural to call polynomials p and q. So we can write p of x is equal to c of x, where this is the quotient, this is the guy I'm dividing by, and this is the remainder, with the key property that the degree of the remainder is strictly less than the degree of the dividing polynomial. Okay, so for when we were dividing natural numbers, the property that held on division was that the number itself, the remainder, was strictly less than the guy we were dividing by. Here, it doesn't make sense to demand that the remainder is less than the guy we're dividing by. I wouldn't expect that to hold for all possible x. But rather, it's its degree that decreases monotonically each time you divide. Okay, and in particular, the polynomials are one instance, as are the natural numbers, of something called a Euclidean domain. And a Euclidean domain is really an algebraic structure where you can do Euclid's method, right? That's what it means. And it's an algebraic structure R. I call it R because the base thing is a ring, which you'll meet in linear algebra next year and in the rings and modules option if you take it. But it's some algebraic structure, a set, that can be equipped with a Euclidean function, something f, that maps from R, except maybe 0, to the natural numbers, which is whatever it is that strictly decreases on division. Okay, so given two entries in the ring, there exist q and r in the ring such that a is equal to qb plus r, and either the remainder is 0 or this Euclidean function strictly decreases. So for the natural numbers, the Euclidean function was just the identity function. For polynomials, the Euclidean function is the degree. And what that means, if you have such a structure, is that you can generalize Euclid's method. And so you can generalize the concepts of greatest common divisors, Diophantine equations, Bézout's lemma, and everything else that follows from Bézout's lemma, like the Chinese remainder theorem, Euclid's lemma, and so on, to such structures. Okay, and so what will we use it for? Well, today what we're going to use it for is computing the common roots of two polynomials. And so we're going to see much more general algorithms for computing roots in subsequent lectures. But today we'll just consider finding roots of polynomials, and in particular computing common roots of two polynomials. So what I can do is, so what are the common roots? They're the x's such that p of x is equal to q of x is equal to 0. And the basic idea is that we compute the greatest common divisor of the two polynomials of p and q. So that's the polynomial of largest degree, that Euclidean function showing up again, that divides both p and q. And there's a link, of course, between the roots and division. So a number a is a root of p if and only if the associated factor x minus a divides p. And this is the link between computing common roots and common divisors. So if we calculate the greatest common divisor and then get the roots of that, that will be all the common roots of our two polynomials. Okay, so let's see an example. And I should first start off with a confession. It's really hard when you're dividing polynomials to keep the coefficients nice, right? What tends to happen when you divide one polynomial by another is that sort of the coefficients are blowing up. And indeed, when you're doing computer algebra systems, there's a lot of work on things like pseudo-remainder sequences and so on to try to contain the sizes of the coefficients that you have to store. But I apologize that just dividing a polynomial by another just isn't a very pleasant task. So here I've written it out for you. So we're going to divide this quartic polynomial by a cubic. Okay, so we write down the steps of Euclid's method. So p is equal to some quotient, which is x, times the thing we're dividing by, plus a remainder. Okay, so far so good. And then we divide this guy by this guy. Okay, so this one is equal to some quotient, and already the numbers are getting, I'd rather integers, but never mind, times the thing we were dividing by, which is this guy, plus a remainder. And of course, each time the degree is decreasing. Here, the remainder was degree 2. Now it's degree 1. And so then we have to stop here. So then we write the division of this guy by this guy as its some quotient times this plus 0. Okay, so as predicted, we've met 0. And so that means that this, the last remainder before we hit 0 is the greatest common divisor. So in particular, if I drop the coefficient in front, which doesn't change the roots, right, then that means that x minus 1 is their greatest common divisor. And so that means now that x equals 1 is their only common root. And you can check that x equals 1 is their only common root by just summing the coefficients, right? So if I plug in x equals 1, you just get the sum of the coefficients in the monomial basis. So it's 1 plus 1 minus 6 plus 5 minus 1. And same here. OK, and so that's how you go about doing Euclid's method for polynomials and how you would compute the common roots of two polynomials. And we mentioned some interesting applications. So the first is that it's a nice trick that if you want to identify the multiple roots of a given polynomial, let's say you have a polynomial, it's too high of a degree to work with, but you suspect that it has some roots that are multiple, then what you can do is you can compute the greatest common divisor of p and its derivative. And the derivative will also be 0 at the same multiple roots. So that means that they will show up in the greatest common divisor. OK? Another interesting thing that you can do that we won't pursue today is that the sequence of remainders constructed by Euclid's method applied to p and p dash can be used to compute its so-called Sturm sequence. Okay? So it involves negating some of the remainders, basically, but you can look it up on the Wikipedia. And the reason why you might want to compute the Sturm sequence is because the number of times it changes sign at two endpoints of an interval can be used to compute how many real roots there are in that interval. So if you want to take an interval of the real line, you want to know how many real roots this polynomial has, you can compute the Sturm sequence, evaluate each of these signed remainders at those 2 points. The number of times that changes sign tells you how many real roots it has, right? Which is really surprising. That's certainly not obvious, right? And it's very beautiful and very clever. Moreover, we can use these ideas of applying Euclid's method to construct or sort of deduce interesting facts about important families of polynomials. So many interesting polynomials are defined via recurrence relations. We'll meet two on the next slide, but maybe you've already met interesting families of polynomials in your studies. And Euclid's method can be used to derive useful facts about them without ever actually computing them. Okay? So in particular, let's just consider a family of polynomials defined via a recurrence relation. So I'll start off with some two polynomials that don't have a common root. For concreteness, let's choose 1 and x, but the x could be something else, right? And then let's construct the next entry of the sequence with this recurrence relation, that it's some alpha, which is a linear polynomial, degree 1, times pk minus 1, plus a constant times pk minus 2. Okay, so that recurrence relation defines a family of polynomials. And without actually specifying what these alphas or betas are, we can show that any two adjacent entries in the sequence must have no common roots by applying Euclid's method. Okay, so before we do this, let's just meet why would we ever care, right? So the main place where I care about it is with these Chebyshev polynomials. So I keep banging on, I'll mention it, I think, every lecture, that you don't want to represent polynomials in the monomial basis, right? But I don't just want to, drag monomials down. I want to tell you what you should be doing, and the answer that what you should be using is the basis of Chebyshev polynomials. And they're defined. You can define them in many ways, but this is one of them, where this is the one I had in mind, where t0 is 1, t1 is x, and tk is a linear polynomial multiplying tk minus 1 plus a constant times tk minus 2. And Chebyshev polynomials are really, really important. So you've already studied Fourier series last term. And Fourier series relates to periodic functions, right? Well, Chebyshev polynomials are sort of the non-periodic analog. More or less every statement that you study in Fourier analysis, expanding functions in terms of a Fourier basis, you can write an almost exact analog of expanding a function in terms of a Chebyshev series instead. So if you have a problem where you don't have a periodic function, but you would still like to do Fourier type analysis, it's Chebyshev polynomials that you use. And these are the main way to represent functions on a computer, and thus every application involving functions, for example, the weather forecast or whatever else, will use Chebyshev polynomials along the way. There's another family of polynomials that I thought I would mention that also fit into this pattern, the Laguerre polynomials. So these, we've met them already in computational mathematics briefly when we looked at the solution of the Schrödinger equation for the hydrogen atom. So these describe the radial part of that wave function. So here now the first Laguerre polynomial is 1. The second Laguerre polynomial is minus x plus 1. That's not exactly the same as on the previous slide, but the important thing is that these two have no common roots. And then we define the next Laguerre polynomial in terms of some linear polynomial multiplying Lk minus 1 plus some constant multiplying Lk minus 2. Okay, and you see that Laguerre died in 1886, whereas the Schrödinger equation and the wave function for the hydrogen atom was only figured out in the 1920s or maybe 1930s. And so this happened 50 years after Laguerre died. So he was studying these polynomials for other reasons, but I'm sure he would have been very pleased to see them show up in something so fundamental. Okay, and so let's just go ahead and prove that for any two entries, adjacent entries in these sequences, that the two polynomials have no common roots. Okay, well, the first thing to say is that the degree of pk is just k by induction. And that's really because we're multiplying by a linear polynomial at each step, and that can only increase the degree by 1, right? So that's straightforward. Okay, and then no more than this, where the recurrence relation defining the Fibonacci numbers also gave the statement of division of one by another. Well, when we divide pk plus 1 by pk, we'll get exactly the statement of the recurrence relation, right? Because this pk minus 1 is of lower degree than what we were dividing by, so this must be the remainder, and this must be the quotient. Yeah. So there's a deep relation sort of between recurrence relations and the statement of division that you use in Euclid's method. Okay, and so then up to a non-zero scalar, this beta k, which I can ignore that because it doesn't change the roots, pk minus 1 is the remainder when pk plus 1 is divided by pk. So then Euclid's method tells us to divide pk by pk minus 1 with remainder pk minus 2, and so on. So every time we make a step of Euclid's method, we'll just go down this recurrence, the sequence induced by this recurrence relation. And so eventually it must boil down to the final statement that p2 is alpha 2 p1 plus beta 2 p0. And then we know what p1 and p0 are. They're two polynomials that have no common roots. And so that means that the greatest common divisor is just some non-zero constant. So there can't be any common roots. Okay, let's leave it there. See you next Tuesday.